right. Hey, everyone. My name is Lee, and I am a Senior Manager of Software Engineering at Capital One. And if I were Robin, then I have Batman here, Moieed Ahmed, who is my co-speaker and also Director of Software Engineering at Capital One within our commercial bank based in New York. Between the two of us, we have worked the gamut of startups, mid-sized companies, and large corporations. Over the last 5 years, we started using Go across all of our teams to build enterprise solutions. We're here today to share generalized enterprise use cases where Go can really shine. These projects span across domains such as cloud, software engineering, and shared services. Before we get going, I want to survey the room. So if you'll indulge me, can everyone please put your hands up if you've been writing Go for 0 years or more? Zero or more. just the fact that you're here means your hand should be up. 5 years or more. Okay, some hands are down. 10 years or more?
How many?
10 years.
Yeah.
Amazing. Most hands are down at this point. 14 years. Final frontier here. All right, and last but not least, what about 20 years? Okay. Just I wanted to make sure everyone's still with me here, so thank you.
The first open source release of Go was 13 years ago.
I know.
So if it's 14 years, you had to be at Google to do that. Sorry.
Yeah. So I noticed that most of us had our hands still up back when we were at 5 or fewer years of experience, and that's great. That means you have used Go enough to have built some things, so hopefully this talk will give you some more ideas next time you take on a project. So why use Go at a large company? Here are 8, but non-exhaustive, but very compelling reasons. First, performance and efficiency. Go's high performance and efficiency is often the top consideration. That's true for startups, and especially so at larger companies. At scale and high traffic, faster build times and efficient execution translates to time and monetary savings. Concurrency and scalability is another compelling quality. With concurrency primitives like Go routines and channels, Go's built-in support for concurrency and scalability is just highly valuable. It's well suited for developing high-performance, scalable systems that need to handle heavy loads. Typing and safety. Go is statically typed, which means type checking occurs at compile time, reducing the chances of runtime errors. This enhances code reliability and maintainability, particularly in large code bases. Built-in safety features, such as memory safety and garbage collection, help prevent common programming errors and enhance security. Simplicity and readability. The simplicity and clean syntax of Go make it easier to write, read, and maintain. Its ease of use and readability reduce the cognitive load for devs, leading to easier code maintenance and debugging. Compatibility and interoperability. I had to practice that. It's a hard word for me to say. This one is true for a lot of the mainstream languages like Java, C#, Python, JavaScript, but it's also the case for Go. Its compatibility with other languages and its ability to integrate with existing systems and libraries written in different languages is attractive, enabling a smooth transition and reducing the need for complete code-based rewrites, which, again, are costly. Standard library and tooling. Go's rich standard library and comprehensive tooling ecosystem provide a solid foundation for development, enhancing code consistency, maintainability, and ease of testing. Community and support. The active and supportive community surrounding Go offers access to knowledge, resources, and libraries, which offer immeasurable, but nonetheless important benefits that are reflected in developer satisfaction, code quality, and overall ability to attract top talent. Long-term viability was the last but not least metric that we value here. Go's strong foundations, continued community involvement, Google's ongoing use and support, and its expanding industry adoption all indicate a positive outlook. And when assessing Go alongside other mainstream languages against these 8 facets, we realize that there's just a very compelling case for enterprises to use Go. So there are 4, again, non-exhaustive categories of projects that larger companies tend to build that Go is well suited for. These types of cloud and what we mean there are applications that serve as platforms for users to interact with through command line interfaces. These types of cloud applications often provide a set of tools, services, or APIs that let developers build upon it. They typically offer functionality such as deployment, orchestration, and management. Choosing a language like Go makes sense for its simplicity, efficiency, and strong support for building command line tools. Software engineering. This category should be familiar to many of us. Refers to the development of software applications, systems, or services. Go's clear syntax here, strong standard library, and simplicity contribute to increased developer productivity. Its focus on readability and minimalism reduces boilerplate code, allowing developers to quickly build software solutions and iterate on them efficiently. Data engineering, projects involving handling, processing, and managing large volumes of data. This category includes tasks such as data ingestion, transformation, integration, and storage. These projects often involve building data pipelines, ETL jobs, data warehouses, or data processing systems that enable organizations to collect, store, and analyze, and derive insights from their data. Therefore, efficient data processing is required here. And last but not least, shared services. This refers to components or services that are built once and are shared or used by multiple applications within a large organization. These services provide common functionalities such as authentication, authorization, logging, or messaging that can be reused across different projects. Besides the obvious benefits of Go's performance and efficient resource utilization, there's also Go's small memory footprint and efficient garbage collection, contributing to the overall performance and responsiveness of it being used in building shared services. So these are just 4 types of projects. They're not meant to be exhaustive, but with that context set, let me pass the mic to Moieed to go over some sample use cases.
Thank you, Lee. All right, quick raise of hands. How many of us feel tired? All right, okay, the ones who did not raise the hands, you guys are the ones who are really tired. This is the last presentation of the day, and the gift for you is going to be a happy hour right after this. So let's get through this together. Good afternoon, everyone. This is Moieed Ahmed. I'm a director of software engineering at Capital One. Today we'll go through a bunch of project examples using Go, where Go really shines in an enterprise setting. You guys can tweak these examples based on your use cases to expand usage of Go within your companies. 2 things before we begin. We'll look at these at an architecture level, so there's no code examples in this presentation. And second one is we'll use AWS. So if you guys have used AWS before, you'll see a lot of different examples using AWS services. First project. So what is the problem statement here? You guys may have done this a lot. Let's say you're building a product, and you may have to build multiple different front ends for this. Let's say you have to build a mobile application. There are different varieties like iOS, Android. You have to build web portals like websites. You have to build desktop clients, and many more, maybe thin clients. How do you solve for this where you have to build a backend that works for all of these different front ends? The answer is a pattern, very known pattern called backend as a service. Essentially what you do is you'll build one backend exposing APIs that can work for all of these different front ends so that you can reuse, underlining reuse across all of these different front ends. Let's take a look at the architecture. We'll go from left to right. On the left, we have a bunch of clients. You have your mobile applications, iOS, Android. You have your websites. You have your desktop applications and maybe thin clients. These guys are talking with the big blue middle box in the layer. That's a bunch of microservices written in Golang. Go fits really well for this use case because the language provides all the functionalities that are required that are shown on those boxes. So you have RESTful APIs that are exposed by these microservices that your clients can consume. They're able to talk to your backend services like authentication, transactions, et cetera, et cetera. You also have orchestration services that can combine data from multiple services and then give it back to the client based on the UI requirements of your clients. Let's take a look at the call out of summary of what is this example and what is Go doing for us. You're able to talk to your backend services, your backend systems. You're able to store and retrieve data from your local data stores. You're able to expose APIs, either RESTful or GraphQL endpoints that your clients can directly consume. You have business logic specific to your business applications. How do you deploy these microservices? We'll use AWS again as a pattern. On the left-hand side, we have two examples that are more serverless, modern way of doing things. And then on the right-hand side, you have a classic server-based deployments. We'll go from left to right again. First one is Lambda functions. Lambda supports Go, and you can trigger it via multiple different ways, like API calls, via API gateway, or SNS SQS triggers, or file drops, or any other event generation. Second is AWS Fargate, which is pretty new for us as well. We're also trying things out and probably scaling it across the enterprise. You can use containers that are deployed on infrastructure that is fully managed by AWS. We don't have to worry about it. AWS manages everything for us. All we need to do is build code, deploy it on a container, and the container runs Go code. On the right-hand side, that's the basic version that we started off with, which was AC2 Classic. You spin up let's say a Linux server and then deploy a bunch of Go services there. Last option is your ECS cluster with a bunch of EC2 instances running Go code in containers. Again, these are all the only solutions. You can tweak them based on your use cases, but these have worked very well for us. What were the key learnings? We saw that Go was really high performing in two different aspects. The APIs were performing within milliseconds. The second one is you can hit it with a lot of TPS, transactions per second, meaning you can hit a lot of volume, and Go peaks much better than a lot of other object-oriented programming languages that we've seen. Second one is it's able to attract both junior and senior programmers. Early in the morning, we saw a presentation with a graph of how engineers are kind of liking Go more. Juniors because it's very quick to learn. Seniors because they have seen a lot of other programming languages that can make things really complex. Go makes things simple. Less learning curve. And then if you want to spin up services in Go, development and deployments take very quick time. So essentially, quicker time to market. Let's go to the next example. The problem statement here is, let's say you're building some products and you have different type of information. We'll take customer data for this example. Let's say you have your customer data, and you have 4 different systems which are storing local copies of customer data across 4 different systems. Let's say my record is in it, all 4 of the systems. My name is the same, but my phone number may be stored differently across all of these systems. So you get a different answer by talking to each of these systems, which means there is a data consistency issue, and you have to build a lot of synchronization services across all of these systems to make sure everything gives you the same answer. How do you solve for this? There is an industry lingo, which is essentially system of record, or SOAR. You'll build one system where all your common data is stored as a shared service, and you will have all your client applications publish or consume data from it. You can communicate with this system via 3 different main patterns. One is RESTful APIs or GraphQL endpoints. Streaming data, publish, subscribe messages. You could probably do something like Kafka. And then batch loads. This is your older way of nightly batch processing, file extracts, and file imports. You could also have lake integrations, if you have any. Let's take a look at the architecture. We'll go from left to right. You have a client apps. Going to the middle box, that's our Go processing layer. You have already seen in the previous example a bunch of microservices. Something new that we're seeing here is stream producers, stream consumers. Let's say your customer record got created or updated. Your stream producer will take that message, put it on Kafka so that your client applications can consume it. Or let's say a customer record got updated in a different system. They'll put a message on Kafka. Our stream consumers will get that data, make us whole. On the top right-hand side, there are a bunch of batch jobs. I haven't blown up this box, but I'll give you how this actually works. You can also implement those batch jobs using Go. Typically, they have been implemented using something like Java, Spark, that kind of pattern. But you can do Lambda functions that can be triggered by a file drop and build step functions that can orchestrate all of these calls for you. This is a very reusable pattern. And essentially what you're doing is ingress and egress out of your system into your system using files and lake. Let's quickly summarize what have we done with Go here. The microservices are able to perform CRUD operations like create, read, update, delete, storage and retrieval of data. We're able to expose APIs that our clients can consume, RESTful/GraphQL based on your needs. Publish, subscribe data using Kafka in this example, but you can switch it out to any other provider that you have. Last is data quality and business logic, things like if you want to do some validations, any business processing like duplicate detection, things like that. Let's take a look at third example. This is a different type of an example, which is more cloud engineering. Our company is mostly on AWS, and we have seen that most developers do not consistently apply roles and policies across all different products. And you may be thinking, I'm not that developer, somebody in my company is doing it, but we all know, sure. So let's say you have to do all of these things across different applications. But developers don't do it consistently. You'll end up with a lot of security issues, security vulnerabilities, and a lot of compliance issues as well. And us being in the financial industry, we are highly regulated, so we need to be compliant. How do you bridge this gap and make sure you're doing it consistently? This is just one solution. You can build a cloud application or a set of services which have APIs and CLI interfaces to validate these rules and standardize them across your entire cloud fleet. Essentially, what would end up happening is all your policies and rules, let's say in this AWS case, it's IAM roles, and then policies across all your services are consistently applied across your cloud architecture. How would you implement this? You would have your clients on the left, and then you can also slap a UI on top of this and say, hey, developers, go copy paste your role or a policy in it, hit validate, and the backend can completely standardize that for you. There are two sets of lambdas shown on this. Pre-processing lambdas, these are essentially screening all the code for you, forwarding the request to main lambdas. The go main lambdas, that's where all the action is happening. They're doing three things for us. One, they're talking to OPA. OPA essentially is open policy agent that can run all your validations against your cloud controls. That's where the meat of the processing happens. Second, you can also do on the top right, you have your data store. You can store and retrieve your temporary results there. Third, you can use CloudWatch from AWS to essentially do logging and then push those logs over to monitoring tools that can essentially do all your monitoring, et cetera, for you, like Splunk, Datadog, et cetera. To summarize in the callout, Go is essentially exposing APIs, storing, retrieving data, backend processing using OPA in this case, but you can switch it out to any other processing that you like, extra logging. And what you can also do is, instead of doing this more of an application-to-application connection, you can also do extra SDKs, packages, and libraries that you can provide to your developer community so that they can just integrate it at development time. You can also do nightly batch processing and internal tooling that are more event triggers. Something like, let's say I want to go into my cloud, validate a section of my cloud and say everything is applied consistently there. I can do that. After looking at all of these examples, you might be thinking, hey, why are we still hanging on to those legacy object-oriented programming languages? Last example from me before I hand over to Lee. This is going back to morning's presentation, so we'll see a linkage there. Let's say you have some backend systems. Let's say you have 3 different payment providers. So one payment system or system of record for credit card processing, one payment system for, let's say, ACH, one payment system for wire processing. You do not want all your front ends or clients to have business logic or understanding of how to communicate with each of these different systems. How do you bridge that gap? You would essentially build an abstraction layer, put it right in the middle between your clients and your backend systems. This would look something like this. The architecture is clients on the left, system of records or the backends on the right. Middle piece is your abstraction layer. In this, we'll use Go for implementing all of our abstraction layer. We see command query kind of APIs. That's essentially your CQRS pattern, command query responsibility segregation. What we're doing in this middle box is abstraction layer handles all the communication with the backend. So front ends don't have to worry about how do I communicate with every single backend. What this makes it easy is you can switch out a payment provider and add a new payment provider. Your clients don't have to worry about any single code change. Or if you want to do a major upgrade across your payment providers, clients don't have to worry about it at all. Everything is managed by your abstraction layer. That's pretty much it from my side. I'll hand it over to Lee to continue the presentation.
We're almost there. So here in this example, a typical problem we see is decisions are dependent on multiple data sources. Some are with different runtimes. Some data sources are real-time, others are batch. So how do you build a service that can reliably pull different data sources? A common solution is to build smaller single responsibility components and introduce something like a step function, if you're in the AWS world, to coordinate your lambdas. This way, your step function will keep your lambda functions free of additional logic by triggering and tracking each step of your application for you. So here's a sample generalized architecture. We'll start from the top, work our way towards the bottom. Imagine you had a fulfillment service for processing applications, and you had a Go Lambda API that was triggered. That's where the gopher is. It then hits the second Lambda, which goes out and hits multiple different data stores. Think about when you're applying for a credit card or any new account. That backend needs to collect credit scores, pull past applications and decisions, verify address, etc. Then it becomes a question of, is the data complete? Do we have all the information that we need to move forward? Did any of the data stores return null? If we have all the data we need, in this case, we can then move on to the next step. And if not, we'll go back and we can customize it to retry every X hours. So in this setup, when you build small single responsibility components using Go, you can net the following benefits, and these are real testimonies from some of the teams that have gone through such an implementation. The package and we could then package and run code locally more easily, reduce the number of vulnerabilities, and in this case, nearly zero, simplify your code, improve code clarity, and last but not least, improve performance. And in the serverless compute world, improvements in SLA also directly translates to meaningful savings. All right, so with 5 examples on the table, I want to highlight some key themes that have bubbled up during both Moieed and my segments during our time together. First, Go is fast. For example, there are tons of Lambda performance comparisons between various languages, and Go consistently outperforms the likes of Python and Java, and often goes neck and neck with certain other languages like Rust. Next, the ease of building and running code locally is a huge enabler for developer productivity. People often don't think about the cognitive cost of developer anguish and churn, but we really should. Go is simple. Simple syntax should translate to better code clarity and improve maintenance, debugging, and quality of life. Go is fun. This makes learning and experimenting with features interesting. We've seen developers who have been writing Java, C#, Python for decades, and they get really excited about learning Go, sharing their findings, learning together, and applying it on the job. And lastly, this is an amazing community. Support is strong, as evidenced by a lot of the presentations we've seen today, and this community is growing, as evidenced by our attendance today. And I would just say, this is Moieed and my first Gotham Go conference. And that fun fact about me, I was an investment banker just 8 years ago, and if you had told me back then that I would be up on the stage speaking to a room of 100 or more about a topic where the language's mascot is a gopher when I was on my way to 383 Madison up in Wall Street, I would have called you crazy and kept on walking to tend to my Excel spreadsheets. So lastly, just if you want to, before we wrap up, just a quick slide about our Capital One's commitment to open source software. We're open source first, which means we develop and consume open source software. Our teams have made thousands of contributions to more than 100 projects, 20 of which are our own. And we invest in this community by sponsoring open source projects. If you want to learn more about us, or our technology or job opportunities, check out CapitalOne.com/tech and CapitalOneCareers.com. Otherwise, you can follow us on Twitter at Cap1Tech. I think with that, we're at time, and hopefully you enjoy our presentation, and hopefully we'll see some of you later at happy hour.